So welcome back to Non-Equilibrium Thermodynamics. This is class number 7. We have been talking about Legendre transforms and some of the properties of those in the context of thermodynamics. In thermodynamics, we don't use the Legendre transform as it's used in convex analysis, strictly speaking. We use the negative of it, but the properties are similar. If we start off with a convex function f generically, then it's some function of x, and we can transform it to a new function called the Legendre transform. Uh, Commonly in the convex analysis literature, it's called f star. It's a function not of x, but now it's a function of its derivative variable p, the derivative variable p. And it's for a convex function, we showed there's a generic definition for all functions, and then we showed that for convex functions, it reduces to this definition here. So the important points here are that we've transformed from f to a new function, which is a function of the derivative variables, derivative variable in quotes. P comes from the range of f prime. So the derivative values of the original function f are where we're drawing the values of p. So the domain of this function is actually the range of this function. So we transform it to this function. We lose no information in doing this transform. And the way we know this is that we can always transform back to the original function without losing any information using the Legendre transform again. So take the Legendre transform of this, that would be the star star function that gets us right back to the f function. The same is true as if we use the negative. If we use the negative, then doing a negative twice gets you back to the original thing. What else do we know about this function f star p? Well, we know it's convex, and that allows us to once again use the simplified formula for the Legendre transform for that function, and that's what, of course, gets us back to f. When we do the f star star, that's just the original function f. So it's an involutory operation. You get the same thing back after doing it twice. And again, you lose no information. That's very important. Now, the functions are not the same. And the example that we went through last time should have convinced you that the functions are not the same. That is, f of x is not the same as f star p. They don't have the same functional forms, but they do contain all of the same information content. None of the information is lost. This is analogous to taking a Fourier transform of a function. When you take the Fourier transform, you now have a function in K space, which looks a lot different than the original function, but it has all of the same information in there. And if I take the transform twice, I get back to the original function. As I said, in thermodynamics, we use the negative Legendre transform. So notice the structure of this transform up here. xp times p minus f of xp, where xp is defined as the value of x that satisfies this equation, f prime is equal to p. So it's that unique value. And the reason why we know it's unique is because this function f prime is an increasing function, strictly increasing. It's a one-to-one onto function. We're going to use the same thing in our thermodynamic context to transform the energy function to what's called the free energy function. And of course, we've got a bunch of variables here. And the question is, how do you apply the Legendre transform? For that, the Legendre transform by definition only involved transforming one of the variables to its derivative variable. The way the terminology of art that we use in convex analysis and thermodynamics is that we transform from an original variable to its conjugate variable. And then, of course, if we transform twice, you go from the conjugate variable back to the original. We want to transform the energy function, which is a function of S, V, and N, by only exchanging its first variable with its derivative variable. The derivative variable, of course, is derivative of u with respect to x, s. That's the temperature function. So we're going to exchange the entropy function with the temperature function. And that's because temperature is an easily controlled thermodynamic variable, whereas the entropy function is not. Okay. Temperature is easy to control, easy to measure, whereas the entropy is difficult to control and difficult to measure, if not impossible. So how do we do this? Again, we're using the negative. So if we use the negative, this plays the role of f. Previously, this was over here, and this variable, this product of variables was over here. So this is the variable that we want to change to. This plays the role of p that we had above. And st, this is the value of s at this value t, or the inverse of this, and that plays the role of xp. Okay? So it follows exactly the same prescription. We're transforming this function of SV and n to TV and n, and it's called, this new function is called the free energy. It has exactly the same structure, except that we're using the minus of the transform. Okay? What is this st variable here? It plays exactly, as I said, the same role as xp plays above. Okay? So it's involved, or it's defined through this inversion. It's defined through this inversion, right? So this is the derivative value here that we want. And we want to know what x value gives us that derivative value. Same here. This is the derivative value. We want to know what value of the entropy through this function gives us that derivative value. So it's exactly the same thing. We're merely transforming from SV and n to TV and n. Our transform only, at least the way we've defined it, only allows us to transform one variable at a time. And so that's why we're only swapping out S and V, S for T. Now, why in the world would we want to do this? That again is because it's easy to control the temperature, and we're going to see that this makes the characterization of equilibrium simpler whenever we're talking about a control of the temperature in a very specific way. So the context or the problem that I want to discuss now is where the free energy function is basically indispensable. Talking about equilibrium whenever we're in contact with what's called a heat bath. So suppose we're considering the usual situation where we've got two isolated systems, and initially they're isolated from each other and from the rest of the universe. So the isolated systems are the alpha system and the beta system. And now what we do is we do the usual thing. We remove the isolating wall. This wall here isolates them from each other so it doesn't allow any exchange of energy, volume, or mass. Perfectly isolating. It's an idealization, right? So no wall in the universe can actually do this, but it's an idealized system. We imagine they're completely separated. They're not allowed to exchange any information whatsoever. No energy content, volume content, or particle or mass content. And now, of course, the usual prescription in thermodynamics is to remove that isolating wall. Okay, so this is some sort of fictitious or uh, um, this is only a barrier in its description. It's not actually preventing anything from moving across it. Okay, so you can imagine this is not even there. Once we remove that isolating wall, now energy can be exchanged, volume can be exchanged, and the numbers of moles of the individual particles can be exchanged. Now, why would they be exchanged? Well, they would be exchanged in order to achieve an equilibrium. So even though thermodynamics doesn't explain how to get to equilibrium, it tells us what the values of it tells us what the entropy should be or how it should look like at equilibrium, right? It should be maximized, and we came up with the conditions that describe this maximization state. So when the entropy is maximized, the temperatures of the two phases should be equal. Now, when I remove this barrier, I'm thinking about these as two phases of the same material, perhaps. For example, molten steel in contact with solid steel. So now the way equilibrium attained is that the temperature of these two phases have to be equal, the pressures of the two phases have to be equal, and the chemical potentials of each one of the individual components in these two phases have to be equal. Once these things are equal, nothing else gets exchanged in the system, and we say that equilibrium is obtained. And again, this was through our postulates that we assumed about thermodynamics. And the most important one here is that the combined entropy of these two systems should be at a maximum, subject to the constraints of the system. Now, suppose that instead of isolating the system from the universe, our composite system is put into contact with a large reservoir of stuff called a heat bath. Okay, so I need to explain pretty clearly what a heat bath is. Um, but just conceptually, it is something we're probably already quite familiar with. So if we have a small experiment and we surround this small experiment with a very large pool of water or some liquid substance, then the water or the liquid substance is going to act as a heat reservoir, heat bath. Okay, and we're going to see what are the implications of having this thing. The heat bath is conceptualized as being so large that any change that or any exchange of information that we have with the system doesn't really change any of the properties of the heat bath because it's so ginormously large. It's a little bit like taking a cup of boiling water, okay, maybe just a liter of boiling water and dumping it into a swimming pool with many hundreds of thousands of liters. The temperature and all the other thermodynamic variables of the system don't change that much by dumping this small amount of liquid into this very vast liquid. Because so that's what a heat bath is like. A heat bath is an otherwise isolated thermodynamic system that is so large that when it exchanges a finite amount of energy with an ordinary, otherwise isolated compound system, its temperature, pressure, and chemical potential changes are so small as to be negligible. Okay. So this would be like uh, so only heat is allowed to be, or only energy is allowed to be exchanged. So this would be like taking a volume, let's say a canister of liquid, and then dipping it into the pool. Well, only heat is going to be exchanged through the edges or the sides of the canister, but no liquid is getting out of the canister, and the volume of the canister is not changing. So only heat energy is being exchanged. So this would be like saying, well, it's being exchanged with a very, very large amount of substance, like the water in the swimming pool. That is a heat bath. Similarly, we can also have what's called a heat pressure bath, and this allows exchanges of finite amounts of energy and volume. But since the bath is so large, that this is going to lead to negligible changes in the original states of the temperature, pressure, and chemical potential for the heat bath or for the heat pressure bath. Or I could think about exchanging all three things, energy, volume, and matter. And this is what's called a heat pressure chemical bath. It's going to allow the exchange of energy, volume, and chemicals and matter. But the bath is so large that any finite exchange with a little bit of uh, energy, volume, or matter with this small experiment isn't going to result in any change with the thermodynamic variables of the bath. In particular, the temperature, the pressure, and the chemical potential aren't going to change very much at all. In fact, the change is so small it can be neglected. All right. So, in a way, we can think about a heat bath or these heat pressure baths or whatever as being just infinitely large in extent. So the picture is like this. Instead of having just two isolated systems, which we're going to open up and allow exchange of energy, volume, and matter, we're going to think about, right? So the normal process is we've got isolating surfaces from the universe and from the two individual systems. Usually we just move this wall out of the way, right? And then we allow exchanges of the two subsystems. But now we're going to put things in contact with this large heat bath, and we're going to see what happens in this case. And the free energy is going to play an important role in the dynamics of this case. So let's recall, and this is going to be important for our analysis, this integrated form of the entropy function. This is also called Euler's equation or Euler's relation. So it says that the entropy function is equal to 1 over the temperature times the internal energy plus pressure over temperature times the volume minus chemical potential over temperature dotted with the n vector. So if you like, you can just think about it as being a single component species. And so this is just single n and the single chemical potential. But otherwise, there's a sum involved here. So this is what we call Euler's equation or the integrated form. I've just put boxes here because this form holds for each one of these subsystems, alpha, beta, and this system up here I'm going to use with a superscript B to mean bath. Superscript B means bath. Now, initially, everything's isolated from each other. The bath is very, very large, right? So this is like the ocean, and this is like a small experiment that we're doing in an ocean. Originally, this bath is at temperature T naught, pressure P naught, and the chemical potential is mu naught. Okay, so originally it's set at those values. It's of course allowed to reach its equilibrium by itself. These are at their equilibriums, and now we're going to think about removing these. We're going to think about replacing this isolating wall and this isolating wall with something else. But this relation holds individually for each one of those sub-environments, alpha, beta, and the heat bath B. Okay. The temperature, of course, is a function of the internal energy, the volume, and the number of moles of each constituent, as is the pressure and the chemical potentials as well. Now, let's think about the system as a whole. In a moment, we're going to remove these walls and think about the flow of certain things. Okay, so we're going to remove this. We're going to replace this isolating wall with a diathermal wall, which is going to allow the exchange of energy only, but not volume or matter. And we're going to remove this wall entirely so that energy, volume, and matter can be exchanged by these two subsystems, alpha and beta. But for now, they're completely isolated from each other. The total entropy of the system is going to be the entropy of the bath plus the entropy of alpha plus the entropy of beta. So once we remove the constraints, then a new equilibrium is going to be established. And how do we know what this equilibrium should be? This new equilibrium should be the maximum of this new entropy function, subject to any constraints that we have in the system. Now, as I said, we're going to remove the isolating wall that was here, and we're going to replace this with a diathermal wall. What's a diathermal wall? So that a diathermal wall simply means it's a idealized wall that is going to allow energy to be exchanged from the bath to the subsystem. Okay. Well, this is now one system essentially. You can think about it as what was formerly two isolated subsystems, but energy can be exchanged across this boundary. It can go both ways, right? It can go both ways, but it's really, really, really large, and these guys here are small. So any energy, volume, well, it can't exchange any volume or matter, but any energy it exchanges with this system is going to change the temperature, the pressure, and the chemical potentials, right? They'll move a little bit, but it's going to be very small and therefore negligible. So again, energy can be exchanged with the system. It can come into the system or out of the system, but it's going to be a very small amount because this guy is so large. And it's going to be so large that the temperature B is going to change a little bit from its original value. Its original values were T naught, the pressure was P naught, and the chemical potential was mu naught. The value is going to change, but they're going to change very slightly and basically imperceptibly. So our system will not exchange, again, not exchange volume or mass with the bath. Only energy exchanges gets exchanged, and that's because we've used this diathermal wall. There's no wall between these two subsystems, alpha and beta, so they can freely exchange um, energy, volume, and matter. So we know that at equilibrium, we know so this system is a system of three subsystems. We could just say, okay, well, we know how to reach equilibrium here. It's just going to be the temperatures have to be equal amongst all subsystems. The pressures have to be equal, and et cetera, et cetera. Well, again, here, since we're only exchanging or allowing exchanges of energy, we know that the temperature across the subsystems have to be equal, and we know that the pressure and chemical potentials for this subsystems have to be equal. Okay, so we know how to characterize equilibrium. But now, again, we're going to argue that the new equilibrium value for this guy is imperceptibly different from T naught, such that we could just replace this value with T naught. Okay? This says that at equilibrium, actually, these two temperatures are also going to be T naught because this guy is not going to be able to change much from T naught. Okay, so the equilibrium temperature, because it changes imperceptibly in the bath from T naught, means that the temperature across the whole system has to be T naught. So alpha, beta, and B can exchange a little bit of energy. So we're not saying that the energies are not changing. We're just saying that the amount that gets exchanged to the bath or from the bath is very, very small. Okay, so but systems alpha and beta can exchange not only energy but volume and mass as well. It's just that alpha and beta don't exchange volume and mass with the bath. So keep that in mind. All right, so now let's go through our usual characterization for finding the equilibrium value of or the equilibrium conditions for this. But now we want to take into consideration the fact that the temperature, pressure, and chemical potential in the bath are not going to be perceptibly changing from T naught, V naught, and N naught. Okay, and so our usual prescription for equilibrium is going to be maximizing the sum of entropies. So we're going to take the entropy of the bath plus the entropy of the combined system alpha plus beta. And the constraints of the system are going to be the following. We're going to allow energy to be exchanged with the bath. Okay, so the total energy budget that we have between alpha, beta, and the bath has to be fixed. This is our conservation of energy constraint. Okay, alpha, beta, and the bath energies have to sum to the total U naught. Whatever whatever energy budget we had to begin with, it's got to be finite. It's just that the energy of the bath should be considerably larger than these two values here. Okay, finite amounts get exchanged, but that's going to lead to an imperceptible change in the temperature, pressure, and chemical potential for the bath. The volume of the two subphases alpha and beta have to add to V naught. We don't care about the volume of the bath because it doesn't get exchanged with the system, and we're really only interested in what is the equilibrium of the alpha beta system in the end. And that's because the equilibrium with the bath doesn't change much. So basically we can just consider it to be always at equilibrium. And these number of moles of these two phases, alpha and beta, for each component I have to add to some value. So this is the constraint set over which we're going to try to compute this maximum. Now, for the bath, we already gave the formula above using the using Euler's equation, the integrated form. And so for the bath, we can just characterize the entropy as almost unchanged. We're not changing its volume. We're not changing the number of moles of particles. And we just got done arguing that T naught, P naught, and mu naught haven't really changed. They don't change enough to warrant any monitoring of them. However, UB can change. This can change a finite small amount of energy with the subsystems. So this means that the entropy of the bath is, to a good approximation, just this term plus this, where we consider this to be a constant. Okay, so the pressure not changing, the temperature not changing, the volume not changing, that means this term is constant. Chemical potential doesn't change, temperature doesn't change perceptibly. Remember, we're saying they do change, but it's just not perceptible. And then the number of moles doesn't change because it's not allowed to exchange any matter with, these really don't change. There's no exchange of volume or matter with the subsystem. So this is a constant, and we only really care about this change here. So to a good approximation, our entropy for the bath, even at equilibrium, is just given by this formula. Again, just I want to hammer home the point. The new equilibrium values that we could obtain by going through our true process of equilibrium don't change much from what the original values were for the bath, T naught, P naught, and mu naught. Now, we're only going to consider changes in the energy because that will be important, how energy is exchanged with the subsystem. So B, we can eliminate this variable by writing this using the constraint that we had above. We can solve this for UB, that variable there, by writing these two variables on the other side. So UB is equal to U naught minus U alpha minus U beta. So we can substitute that in there. So this gives us an expression that only involves information about the subsystems U alpha and U beta, right? I just replaced UB with that. Now, this value here, U naught over T naught, which we gain from this term here, can be lumped together with that constant that we had above. We called that constant C1. I can call this new constant C2, and it's not going to change at all. U naught is a fixed value. These changes here, right, we want to keep track and we want to monitor how equilibrium is achieved in the alpha beta system particularly. And so exchanges between the two systems are going to be important. In fact, it's not negligible how much energy is exchanged among those two systems. All right, so this gives us an expression for the bath, the bath's entropy, but now we've eliminated any variables that have to do with the bath except for the temperature. And that was the initial temperature, and we're arguing that it's also the final temperature. Okay, so we just put that expression into the total entropy function, the thing that we're maximizing, subject to constraints. And what we're calling the equilibrium entropy is that entropy that is obtained when we've achieved equilibrium. Okay, so this is the entropy function. We're going to maximize that, and whatever its maximum value is, we're going to call the equilibrium entropy. All right, but there's a constant here that doesn't get involved with the maximum, so we can bring that out. So we're taking only the maximum of what's left inside. That characterizes equilibrium, certainly. But we view this guy here is just an expression that is essentially defining or has in it the free energies, right? So now we're going to use the fact that we know that for both of these expressions, that the free energy, and I'm going to just write a box therefore, that's just equal to U minus TS. U minus TS. I'm writing this more or less the way the physicists would do it. I'm not concerning myself carefully with what are the values of S given a certain value of T, right? Okay, so I'm using a more or less shorthand way of writing this. So notice that if I multiply both of these terms by T naught and then divide them by T naught, the expression doesn't change. But what I get on the top is just going to be minus the free energy of alpha plus the free energy. This is a error here. This should be the free energy of beta. And I think it's missing a tilde, so I'll put the tilde back. Okay. Now, the temperature is a constant now. I can bring that out front. And I might as well bring the minus sign out front as well. So this comes out as minus 1 over T naught. But what happens if I bring out a minus, okay, for an object or a function that I'm trying to maximize? Well, the maximum now is characterized by a minimum. So in other words, the maximum of negative of function is minus the minimum of that function. So that's all I'm doing there, right? If I bring out this minus sign, I have to switch this maximum to a minimum. All right, now I've brought this function or this variable out. I brought the minus sign out, and now I'm just going to expand these two things here. Now each one of these functions is a function of T naught, but T naught is fixed because T naught is the temperature that is kind of decided for us from the bath. V alpha and V beta, what are those? Well, we don't know because those can change in the process of equilibrium. Volume can be exchanged between the two phases, as can be the number densities, or sorry, not the number densities, but the number of the moles of each substance. Those can also change, but they're subject to constraints, right? So what have I done in this situation? What I've done is I've essentially shown that finding the equilibrium of a material that's in contact with a large bath is essentially the same as minimizing the sums of the free energies of the functionals, free energies of the subsystems, alpha and beta, with these two constraints, volume constraint and the number of moles constraints, where temperature is entirely fixed. And why is temperature fixed? Temperature is fixed through the heat bath. So this gives us another expression for equilibrium, which is quite useful to us. Why is it useful to us? Well, we can, these situations where we have a small experimental setup in contact with a heat bath that's basically how we control temperature in a thermodynamic experiment. If we want to say we're examining this process, but it's at constant temperature, what the heck does that mean? That means that the experimentalist is putting the experimental apparatus in contact with a large heat bath. What is that large heat bath? Well, it might be a swimming pool, or it might be in a freezer where the temperature is held at 2 degrees Kelvin above zero. So that's what that means. That means if they're saying the temperature is controlled in the experiment, that it's essentially in contact with a heat bath. Well, what does that mean thermodynamically? Well, what it says is that you can come up with this new thermodynamic function called the free energy, which is useful in these cases where you're in contact with a heat bath. Why? Because the temperature there is fixed. It's a fixed variable. And you might say, well, I haven't really gained anything. Well, the truth is actually you have, because you've exchanged with other variables that you may not be able to control, like the entropy. You don't have control over that. You might not be able to control some other variables, but you certainly can set the temperature of the heat bath. And if that's the case, now to find the equilibrium values or the equilibrium state, we know that temperature is not going to be involved with that. Temperature is fixed. What are the other variables in the system that we have to look at? Well, the other variables in the system that could be important to us are the volume and the number of moles of the individual species in the experiment. Those are still under constraints. Those are still under constraints. So this gives us a postulate that we can. So if you don't like the hand waviness, I guess, of all of this, I didn't write this as a theorem because I really think about this as a new postulate for equilibrium, where I'm in contact with the heat bath. I could, and the reason why I didn't write it as a theorem, coming from the definitions of what it means to be in equilibrium, and then using the definition of a heat bath, is because that's all kind of nebulous. So I want to build that kind of hand waviness that I would write or put into the definition of heat bath. I've just decided to put it in terms of a postulate. And here's what I mean. So consider a compound, otherwise isolated thermodynamic system in contact with an otherwise isolated heat bath at temperature T naught. Actually, should not just be temperature, but there's pressure involved as well in there. Pressure and chemical potentials, right? The equilibrium of a compound system is the state satisfying the isothermal condition. Why is it isothermal condition? Well, it's because it's in contact with that heat bath, and so the temperature is controlled. The heat bath is setting the temperature of the system. And it's that state satisfying the isothermal condition, which minimizes. Why is it minimization? It's minimization because whenever we were working with a maximum because we were working with entropy before, but now that the negative appears, we bring that negative out. That changes a maximum to a minimum. Okay, so that state, which is satisfies the isothermal condition, which minimizes the sum of these two free energies. And why is it the sum of the two? It's because those are the two free energies that appear above, just that of the state alpha and the state beta. What happens to the free energy? You might say, well, where's the free energy of the bath? That's not important for us. We're focusing on the equilibrium of the system for the two isolated or originally isolated subsystems, alpha and beta. The heat bath is so large that we don't really have to consider its conditions for equilibrium. That's the whole point of this. So it's that state which is isothermal, which minimizes this function, the sum of these two functions, subject to the following constraints. V alpha plus V beta has to be equal to the total size of the container. Which size of the container am I talking about? I'm talking about the size of this container, right? Because I'm allowed to change volume with alpha and volume with beta, but not with the bath and not with anything else in the universe. Okay. Only energy is allowed to change, be exchanged. So that's the volume constraint, alpha and beta volume summed together. And then the mass constraints or the matter constraints, Ni alpha plus Ni beta has to be equal to a constant Ni naught. Okay, so since the systems alpha and beta can exchange energy with the heat bath, in this system, energy is not conserved in alpha plus beta. Okay, so this might be a bit of a stumbling block for you because in our previous considerations for equilibrium involving the equilibrium of two subsystems, alpha and beta, we had conservation of energy. So now what happened to the conservation of energy? It seems like it's gone out the window. The truth is that it hasn't gone out the window. We could still measure how much energy gets exchanged with the heat bath. It's just that the heat bath is really not the important part of the system. The heat bath is just something there to set the temperature. So energy in the system, B plus alpha plus beta, will be conserved, but I don't know what is going to be the energy of alpha plus beta. So if I start out with an initial energy budget for alpha and beta, that could be lost to the system, to the heat bath. Okay. So I could end up with more energy than I started with, or I could end up with a lot less energy than I started with. Here's one way in which the energy content of the system could could be increased from the heat bath. Suppose that I have a very cold system to start with. Suppose this system here has a very low temperature compared to this guy. Well, this is going to, that means that to get this thing to be isothermal, it's going to pump in some energy from the bath. But the bath is really large and it's got a huge energy budget. So it's not going to miss that energy. However, the subsystem sees essentially a lot of energy pouring into it to warm it up. Okay, so if this temperature is really low, then we know from class number 2 or 3 that energy is going to flow from the hot body to the cold body, warm it up, so that the energy of the original system, alpha plus beta, might be a lot bigger at equilibrium than it is at the start of the process. Okay, so that's my postulate for equilibrium when we're in contact with a heat bath. What's the idea? The idea is that it's more useful. The big idea, I suppose, is that it's more useful to use the free energy in this characterization. We don't know what the energy is going to be. The energy could be, we could lose a lot of energy to the heat bath, or we could gain a lot of energy from the heat bath. We're not as interested in that. We're interested in the state otherwise for the system to reach equilibrium. Okay, so that's going to be to find equilibrium. We're going to therefore find the variables that minimize this function here. What are the natural variables for this system? Well, T, but that's already fixed for us, then volume, then the number of moles, right? So once we figure those things out, then we'll know the equilibrium of the system. All right. So you may recall a few classes ago, we talked about the equations, how they're transformed whenever the total number of moles is fixed. And we use this and the homogeneous of degree 1 property to define what we called molar values of these the other quantities left. So these are quantities that are defined by dividing out the number of n, which is fixed. So we obtain the molar energy, the molar entropy, and the molar volume. Now we're going to do the same thing with the volume that we did with n. Um, we're going to imagine a fixed volume v, and we're going to define, instead of molar values of quantities, we're going to define densities of values, okay? Or the amount of that stuff per unit volume or per volume. So let's suppose that V is fixed and we're going to define the energy density, okay? This is energy per volume, U divided by V. So this gets this lowercase variable U. Previously, we used the same lowercase variable for the molar quantity. So be careful here. We can't introduce another variable. We have to stick with this one. So we're going to overload it and redefine it. Okay, so the energy density is defined as U divided by this fixed volume V, and volume is positive, of course. We're also going to define what's called the molar density. So this is the number of moles per volume. Okay, so anything which is number or quantity per volume, this is called a density. Now, because of the fact that S is a homogeneous function of degree 1, we know that this is true. That's by definition. What we're going to use here is, instead of using a generic lambda, we're going to use 1 over V. Okay, and I'm going to get rid of this page. Scratch page. Okay. Okay, so 1 over V times the entropy function using homogeneity of degree 1 means that this function is actually going to be a function of only 2 variables, the energy density and the mass density. Okay, V over V is of course 1. And now we're going to introduce a new entropy value called the entropy density. Is the entropy per volume, entropy density function. It's a function only of U and rho, lowercase u and lowercase rho, and it's defined as this quantity, because this is really only a function of 2 variables. Okay, and then of course, just using the fact that this is defined this way, multiplying both sides by that V, and we get this simple relation. If I have the entropy density and multiply it by V, I get back to the original entropy. Likewise, if I started out with defining the entropy density and the same mass density, I could construct an energy density function, which is a function only of the two variables, s and rho, and I could come up with a similar relation for this new energy density function. Okay, using exactly the same expressions that I had above. Of course, we can go through and play the same game that we played last time. So this is the same example, really, except that we're using the density version rather than the molar version. So I have this expression for my entropy. It's pretty easy to show. This is a function, of course, of u, v, and n. If I look at the function, which is only a function of u, 1, and rho, obtained by simply replacing u by its density, the volume by the number 1, and n by rho, then of course you get this function here. And it's pretty easy to see if I multiply that function times v, then I get the original entropy expression that I started with. So there's nothing super sophisticated about any of these manipulations. It's more or less the same as the manipulations that we had whenever we did this with the molar case. Recall that the temperature is a homogeneous of degree zero function. And so if we introduce the same, using the same idea, suppose that lambda is now 1 over v, then this becomes the entropy density. V over v is 1, and n over v is rho. That's the mass density. So we could come up with a new expression for the temperature when we only had two variables, but we're going to abuse the notation that we have and say, okay, well if I only write this temperature, this energy version of the temperature as an expression of these two lowercase variables, then we really understand that it's the same as the temperature of expression for the three variables. It's just that the entropy is replaced by the entropy density, volume is replaced by 1, and n is replaced by rho, right? Same sort of story as before. We can also do a similar sort of analysis. We can change the Euler and Gibbs-Duhem equations to their density forms. Again, this is really the same that we did with the molar case, and so there's not much new content here, except that we're doing it slightly differently and using instead of normalizing by n, we're now normalizing by v. That's it. So if we start off with the original Euler expression, we have that, right? So all I'm going to do is divide both sides by V, and I'm going to use the fact that the temperature, pressure, and chemical potential are homogeneous of degree zero, okay? Homogeneous of degree zero. And the rest of the variables are homogeneous of degree one. But when I divide both sides by V, this becomes the energy density, energy density function. S over V, that's entropy density. V over V, that goes away. N over V, that's just equal to rho. And now I'm going to use that homogeneous degree 1 property to rewrite these functions. It's just functions of the two variables, lowercase s, lowercase rho, right? And of course, this is from an expression I had above. So this is the transformed version of my Euler equation. Transformed version of the Euler equation. And it's exactly of the same form, or almost exactly the same form, as the molar version that we derived, what, 2 or 3 classes ago, right? This is just called the density version. Or I don't know if that's a universal expression, a universal name, but that's what I'm calling it. So hopefully this is familiar to you. How do I get the Gibbs-Duhem relation? Well, remember Gibbs-Duhem was you just use the Euler equation and you use the first and second law expression in differential form to get it. So what I'm going to do is I'm going to take a path in density space. By density space, I mean uh, entropy density and the number density. So I've got this path through state space. And now just using chain rule and knowing that lowercase u, the energy density is a function of the entropy density and the number density of moles, and taking the derivative with respect to the parameter of that path and using chain rule, I just get these two terms. Now, I recognize that the derivative of U with respect to S is the temperature, whether it's in the molar form or the volume form or the regular form, that's just always going to be temperature. The derivative with respect to rho, that's going to be the same as the chemical potential. Okay. Now this is something that has to be shown, but it's true. So that gives us a combined expression of the first and second laws. Remember, this is kind of inexplicably called that. It's kind of an elevated title, but really all it is chain rule and multiple variables. Now the next thing you do is you differentiate the Euler equation using a path and differentiating with respect to the path variable. So plug all those values into the Euler equation. Plug this path into into here and all of these locations as well. Now, in this case, S rho, that's just going to be this path gamma. Okay, take the derivative of that. I'm going to keep that together. I'm just going to call that S and rho together. Just call that gamma. I'm going to have taking the derivative of the first term. The first term is a product, so I have to use product rule, right? And I get for each term two terms, except for what? Let's see. That middle term is only a singleton. Why is it only a single term? Because there's no v variable there. It got divided away. Okay, so when I take the derivative, I'll have two terms for this one for this one, and two for that one. So five total terms. And there are my five terms. One, two, three, four, and five. And now all I do is I'm going to take this expression and subtract it from this expression. These two terms go away right away. That gives me my zero. And what remains are these three terms. This gives me the expression called the Gibbs-Duhem equation. But now it's entirely in what's called the density form. So the same thing can be done for the entropy. So I'm not going to belabor this point at all. It's the same sort of idea. You start with the Euler equation for the entropy, but you transform it into the density version. So I'm going to leave it to you as an exercise, and please do this exercise. See if you can figure out how to get this expression. Then you need the first and second law expressed in a kind of path form. You differentiate you take a path in density space. Now, this path in density space is going to involve the energy density and the number density of particles. Okay, that's the path that you need to take there. What? Now I differentiate this. I get that result. I subtract this result from it, and that gives me an expression for the Gibbs-Duhem equation in density form. Okay, so I'm going to leave this as an exercise for you to do that. Now, what I hope to accomplish in the next 10 minutes is to show you how the free energy changes when I want to write that as expression or as a combined expressions in density form. Okay? So remember, what is the definition of the free energy? So we only gave one definition of the free energy. There are a couple of different definitions, and I'm not sure why I did this, but I used E here. Why did I use E? E is a commonly used variable for the internal energy. I must have been reading another book, uh, and that's why that expression came about. Yeah, I did this in a lot of places actually. So This happens, especially as you get older. You forget. This should have been the internal energy U. Let me just correct this quickly, and hopefully it's, man, it is pervasive. Internal energy is U, not E, Steve. Okay. U and another U. And I hope that that's it. I hope it's confined to a single proof, but you never can tell. Okay. So the free energy, the Helmholtz free energy is defined using the minus of the Lejeune transform as we've done it before. And I'm not going to go through this proof because we don't perhaps have time to do it. So I want you to go through it and make sure, of course, that you understand or make sure that I've changed and corrected all these functions from E to U. Should be U because we're using U as our internal energy variable. So this is, of course, our definition. And what I'm trying to show with this theorem is that this F is kind of a weird function. It's not homogeneous of degree one in the same way that U is. If I have, well, let's start with this side. If I multiply F times uh, an arbitrary parameter lambda, which is greater than zero, how does that move into the variables? So if this were truly a homogeneous a degree one function, then what we've said many times is that, well, that would just, this lambda basically comes in and multiplies each one of the three variables. That's not what happens for the free energy, though. And that has to do with the fact that t itself is a variable which is homogeneous of degree zero. When this lambda comes inside, it only comes inside and attacks or attaches to the volume and the number of moles terms. It doesn't come in and attach to the temperature function. And again, this has to do with the fact that the temperature is a homogeneous of degree one function. So overall, what is this function f? It's not homogeneous to degree one. It's not homogeneous to degree zero. It's just its own sort of thing, and it satisfies its own sort of property, namely this. It's kind of a combination of a function which is homogeneous of degree zero and homogeneous of degree one, I guess. Maybe that's a way of looking at it. I'm not sure. But in any case, it's not homogeneous of degree one anymore. So the proof is kind of long. Took me a while to get through it. I'm going to leave it to you to go through that and make sure that that proof is correct. Let's see. I don't like the look of that one. No, that looks a little bit better. But I hope it's all there. It may be a complicated proof to read, but please do read it and let me know what you think about that. All right, so we've defined the energy density, the entropy density. How does the free energy transform, knowing what we know about this function, right? So what do we know about this function? We saw that it's no longer a homogeneous of degree one function. It's kind of its own weird thing. So how does this affect things when we want to define the density? So let's try it. So suppose that V is fixed, and we're going to define as before this this number density, and suppose that we've only got, it's a unary material, so there's only one number density to be examined. And so suppose that lambda is greater than zero. So we know that from our previous theorem that this is true, but now suppose that we take lambda be 1 over v. Well, it comes in for this function, right? This 1 over v, and it doesn't attach to t, it only attaches to v and n. So v over v is 1, and n over v, that's just equal to rho. So this says that this function, the free energy function, transforms this way when we want to compute a density. This is what we're usually going to call the free energy density function. So that gets a lowercase f symbol like we've had before. Free energy density is equal to this function f of t, 1, and rho. The temperature doesn't change because it's a homogeneous of degree 0 function. So in other words, it doesn't make sense to define something called a temperature density, right? All the rest of the stuff you can define and make a density of it. But a temperature density doesn't make any sense. That's kind of why this works out this way. So then it follows that if I multiply, right? So I've just defined this object here to be this new function lowercase f, which is the free energy density. And so now if I just multiply both sides here by v, then I get this. So this says that if I want to get from the free energy density back to the original free energy, I simply have to multiply through by the volume. Okay. We're going to use the Helmholtz free energy a lot in this course. And so I wanted to show you how this free energy density comes up. So I know, for example, in Sam's work, he uses free energy density all the time. And some of the rest of you who work with me are using free energy densities. That's where this thing comes from, the thermodynamic framework. It's defined in this way, and to get back to the original free energy, you simply have to multiply by V. Or if it really does vary from point to point, then the way to get back to the original is to integrate over the volume. Okay, so if I integrate the free energy density, that gives me the total free energy. In this case, I'm thinking about this as being not a function. Well, I'm thinking about this where t and rho are not functions of space, but momentarily as we get deeper into the weeds of non-equilibrium thermodynamics, we're going to come into the situation pretty quickly where the temperature and the density functions are going to be functions not only of space but also of time, and we're going to be cooking up some differential equations to figure out how to solve for these functions like the free energy density. But of course, all of that's coming a little bit later in the course. So I think, yeah, I successfully made it through these notes. The one omission here that I'm sorry about is that I didn't get to go through this proof in detail, proof of 7.3. So again, for the sake of time, I'm going to leave this one up to you to read through. Make sure that you know how to prove this thing. Again, it's not a homogeneity property. It's kind of like a hybrid property. But in any case, with that, I will end the lecture and take your questions.